In November of 1986, a spacecraft called Voyager 2 flew past the planet Uranus, and for the very first, and to this day still the only time in human history, an instrument built by human hands got a close, direct look at that strange, sideways spinning world. What it found confused scientists so deeply that the confusion simply sat there, unresolved. For the next 38 years, Uranus appeared to be doing something that should not have been physically possible, generating intense, energetic radiation belts around itself with no visible source of the particles needed to actually create them, like finding a raging bonfire with no fuel anywhere near it. For nearly 4 decades, that contradiction simply stood, an accepted, permanent oddity attributed to Uranus itself, treated as proof that this particular planet simply broke the normal rules. Everywhere else in the solar system seemed to follow. Then, in November of 2024, a team of NASA scientists went back through that 38-year-old data one more time. And what they found did not just solve the mystery. It revealed that almost everything scientists thought they understood about Uranus for the past 4 decades may have been based on a genuine fluke, a strange twist that is still actively reshaping how researchers think about that planet's moons right now in 2026. This is the story of what Voyager 2 actually saw in 1986, why it took 38 years to understand what really happened, and why the answer is opening up an entirely new mystery of its own. To understand why this discovery genuinely matters, you first need to understand just how singular and unrepeatable that original 1986 flyby actually was. Voyager 2 remains to this day the only spacecraft that has ever visited Uranus. No orbiter, no follow-up mission, no second flyby has ever been sent in the 38 years since. Everything scientists have directly measured about this planet, its magnetic field, its radiation environment, its unusual moons, comes from that single brief encounter, a flyby lasting only a matter of hours, as Voyager 2 sped past on its way toward Neptune and, eventually, interstellar space. Whatever Voyager 2 happened to record during that one narrow window became, by necessity, the entire foundation of human knowledge about this planet's space environment, a foundation nobody has ever had the opportunity to double-check with fresh, independent data. During that flyby, Voyager 2's instruments detected something that immediately struck scientists as deeply strange. Uranus, like Earth and every other major planet with a magnetic field, is surrounded by a protective magnetic bubble called a magnetosphere, a region of space shaped and controlled by the planet's own magnetic field, shielding it from the constant stream of charged particles flowing outward from the sun in the solar wind. Within that magnetosphere, Voyager 2 detected surprisingly intense electron radiation belts, regions of energetic, trapped particles similar in basic concept to the well-studied Van Allen radiation belts surrounding Earth. The problem was that these belts appeared unusually active and energetic, with no clear source anywhere nearby capable of actually supplying and sustaining that level of particle activity. Scientists searched specifically for plasma, mixtures of charged particles that should have been streaming from Uranus's 5 major moons, icy bodies that, based on comparisons with similar moons found around Saturn and Jupiter, ought to have been continuously venting charged water ions into the surrounding magnetic environment. Voyager 2's instruments found essentially none of that expected plasma. The radiation belts were vigorously active, but the obvious fuel source that should have been feeding them was nowhere to be found. Faced with this contradiction, scientists at the time reached the only conclusion the available evidence seemed to support. If Uranus's major moons were not producing any detectable plasma, the most straightforward explanation was that those moons simply were not geologically active at all. Cold, inert, frozen bodies with no ongoing internal processes generating the kind of venting activity seen on more active icy moons elsewhere in the solar system. For the next 38 years, this became the standard, accepted scientific picture of Uranus, an outlier planet with an oddly overactive magnetosphere and a family of moons written off as geologically dead. An interpretation that shaped how an entire generation of planetary scientists understood this distant, strange, sideways spinning world. That interpretation began unraveling in November of 2024, when a research team led by Jamie Jasinski of NASA's Jet Propulsion Laboratory decided to go back through Voyager 2's original 1986 data with fresh eyes, applying analytical techniques and comparative context that simply had not existed at the time of the original flyby. Publishing their findings in the journal Nature Astronomy, Jasinski's team identified something the original analysis had entirely missed. In the days immediately preceding Voyager 2's arrival at Uranus, the planet had been struck by an unusual temporary burst of intense solar wind activity, a surge of charged particles streaming outward from the sun that dramatically compressed Uranus's entire magnetosphere, squeezing it down to a fraction of its normal size in the days right before Voyager 2 actually arrived to take its measurements. Jasinski described the significance of this timing in remarkably direct terms. If Voyager 2 had arrived just a few days earlier, he explained, it would have observed a completely different magnetosphere at Uranus entirely. According to the team's analysis, the specific compressed conditions Voyager 2 actually flew through occur only about 4% of the time, meaning the single, unrepeated dataset that has shaped nearly 4 decades of scientific understanding about this planet was gathered during a genuinely rare, atypical moment. A 1 in 25 kind of coincidence, rather than during anything resembling Uranus's normal, everyday magnetic environment. This discovery did more than simply explain an old anomaly. It fundamentally rewrote the logic behind the entire original mystery. The intense solar wind event compressing Uranus's magnetosphere in the days before Voyager 2's arrival would have actively driven existing plasma out of the system entirely, physically squeezing it away before the spacecraft ever arrived to measure it, while simultaneously injecting fresh energy directly into the planet's radiation belts, temporarily supercharging them in the process. In other words, the specific combination that had puzzled scientists for 38 years, energetic radiation belts paired with an unexplained absence of plasma, was not evidence of some permanent, bizarre property unique to Uranus at all. It was a temporary snapshot of a planet caught in the immediate aftermath of a passing solar storm, its normal magnetic environment squeezed and disrupted in a way that happened to align purely by chance with the exact narrow window during which the only spacecraft ever sent there happened to be looking. Here is where the story turns from simply solving an old puzzle into revealing a genuinely new one, and this is the part of the discovery that carries real, ongoing significance for how scientists currently think about this distant planetary system. If the missing plasma in Voyager 2's original data was actually a temporary weather-related absence rather than genuine permanent evidence of inert, lifeless moons, then the entire foundation for believing Uranus's 5 major moons were geologically dead may simply be wrong. Researchers involved in this new analysis have stated plainly that it is now entirely plausible these moons have actually been venting ions into their surrounding space all along, just as similar icy moons do elsewhere in the outer solar system. And that Voyager 2 simply happened to fly past during the one specific narrow window when a passing solar storm had temporarily swept that evidence away before the spacecraft ever arrived to detect it. This matters enormously because the question of whether these particular moons showed genuine ongoing geological activity connects directly to some of the biggest, most actively pursued questions in modern planetary science, the search for potentially habitable environments elsewhere in our own solar system. Icy moons that show evidence of internal activity, venting material from a subsurface source, are treated as considerably more scientifically interesting candidates in the ongoing search for environments that might support some form of life, compared to moons confidently written off as cold, dead, and completely inert. For 38 years, Uranus's major moons sat in that second, less compelling category, based entirely on a single, brief flyby that has now been shown to have captured genuinely atypical conditions. This new research does not prove these moons are actually active. It does something perhaps more significant for the actual practice of science. It removes the specific evidence that had been used to confidently rule that possibility out, reopening a question that had been treated as settled for nearly 4 decades. It is important to be precise and honest about exactly what remains uncertain here, because that precision is exactly what separates a genuinely significant scientific development from manufactured hype. Nobody involved in this new analysis is claiming to have directly detected evidence that Uranus's moons are geologically active. What they have shown is considerably more modest, and in its own way, more scientifically important, that the original evidence used to declare those moons inert was gathered under conditions now understood to be unusual and temporary, meaning the confident conclusion built on top of that evidence no longer holds the weight it once did. The genuine answer to whether these moons are actually active remains unknown, and will likely remain unknown until a future spacecraft is actually sent back to Uranus to gather fresh, independent data under a broader range of conditions, rather than relying on a single, brief snapshot captured by chance during one narrow window in 1986. That future mission is not simply a hypothetical dream sitting on a distant wish list. The National Academy's 2023 Planetary Science and Astrobiology Decadal Survey, the formal rigorously researched document that guides NASA's long-term mission priorities, specifically identified a dedicated Uranus mission as one of the highest priority large-scale planetary science efforts for the coming decade. Precisely because so much about this particular planet and its system of moons remains genuinely unresolved, hanging entirely on data gathered during that single, brief, and now recognized to be atypical flyby 38 years ago. Planetary scientists studying Uranus have been explicit that resolving these lingering questions about the moon's true geological state, about the planet's actual typical magnetic environment, will require exactly this kind of dedicated future mission, capable of observing Uranus across a broader range of conditions and over a considerably longer period than Voyager 2's brief several-hour pass ever allowed. Step back and consider what this entire episode actually demonstrates about how scientific understanding genuinely evolves over time, because it is a genuinely important lesson that extends well beyond Uranus itself. For 38 years, an entire generation of planetary scientists worked from a specific, confident interpretation of what Voyager 2 had found, an interpretation that shaped textbooks, research priorities, and the broader scientific consensus about an entire planetary system. That interpretation was not the result of careless or sloppy science. It was the most reasonable conclusion available at the time, built from the best data anyone actually possessed. And it turned out to be built on top of a genuine, unrecognized coincidence, a rare, temporary solar weather event that nobody analyzing the original data in 1986 had any way of identifying, simply because the tools, the comparative context, and the decades of additional solar wind research needed to recognize that specific pattern did not yet exist at the time. This is precisely why old spacecraft data, gathered decades ago by missions long since retired or destroyed, remains genuinely valuable for active, ongoing scientific research today. Voyager 2 has not visited Uranus in 38 years, and never will again. And yet the data it gathered during that single, brief flyby is still, right now in 2026, actively being reanalyzed, reinterpreted, and used to overturn conclusions that had stood essentially unchallenged since the moment they were first published. Somewhere in an archive, decades-old measurements are still capable of producing genuinely new scientific results, provided the right researcher, with the right new tools and the right new context, eventually goes back to look at that same data with fresh eyes. So here is where this genuinely stands right now in the middle of 2026. The specific mystery that puzzled scientists about Uranus for 38 years, energetic radiation belts with no apparent source of fuel, has a solid, well-supported explanation. A rare solar wind event that happened to compress the planet's entire magnetosphere in the exact narrow window Voyager 2 flew through. But solving that old mystery has opened a new one, considerably more consequential than the original puzzle it replaced. Are Uranus's major moons actually geologically active, quietly venting material into space the entire time, exactly the way similar icy moons elsewhere in the solar system are known to do? Nobody currently knows. The evidence that once seemed to rule that possibility out has been shown to rest on a single, atypical moment in time, and the genuine answer will likely have to wait for a spacecraft that has not yet been built, funded, or launched, aimed at a planet. Human beings have only ever visited once, 38 years ago, for the space of a single afternoon. If you want to know when a new mission finally returns to Uranus, and whether those 5 distant moons turn out to be quietly alive with activity after all, subscribe and turn on notifications, because this is a genuine mystery still waiting for its answer. And the only spacecraft that has ever been close enough to check left us with a single incomplete snapshot nearly 4 decades ago.